Hi my dear students, welcome to one more amazing session from Chaitanya Academy, and this is Suresh, Faculty of Chemistry, and today we are going to discuss the most amazing topic from CBSE examination as well as NEET examination, bonding in complex compounds. Definitely for sure I am going to tell you आज सेशन से आपको मिलेगा नीट एग्जामिनेशन में कम से कम एक क्वेश्चन and 2 questions are there will be in the CBS examination. Ready to just start with bonding in complex compounds. So this complex compounds is a chapter I want to take into the 2 parts, and yesterday we completed about IUPAC nomenclature and isomerism and basic terminologies we have. So those students, before going for the session, chill in the examination pressure. In this examination time, definitely you will be having various types of pressures, and if you want to prepare because of this pressure, the revision is also not happening in a proper way. So no worries here, just stay in the live class, take a pen and paper and enjoy the session, and a proper revision bhi kar raha hu main, and Sunita Devi is there. So my dear children, and I strongly believe these academic sessions that we are delivering from our side, building up the students' confidence and the increase in the rank and the marks. And here I believe that you admire teachers from the Infinity Learn and will follow the same. Please, those who are online, please like the session, share with your friends and subscribe to Sri Chaitanya Academy Infinity Learn NEET YouTube channel. Okay, so before going for that, we have 3 kinds of theories we need to talk about in this complex compounds: Werner theory, Valence Bond theory and crystal field theory. These 3 theories we will be discussing, and those who are online, keep discussing your doubts in the chat box and everything we will be discussing. So according to Werner's theory, the metal in the complex compounds has 2 types of valencies. One is a primary valency, another one is a secondary valency. Hi Pankaj, good afternoon, hello. Please like the session. I request you guys, please like the session. What is a primary valency? What is a secondary valency? Look at this, ligands linked by primary valency, metal and the ligand, and there is a link. These valencies of 2 types, primary valency and secondary valency, and this primary valency is a ionizable valency, secondary valency is a non-ionizable and coordinate valency. And primary valencies are normally ionizable and are satisfied by negative ions. If you see MnH2O6 and Cl2, and anything outside the square bracket is satisfied by counter ion, that counter ion is given as a primary valency. And let us talk about the primary valency. Here the primary valencies are indicated by dotted line and the secondary valency is indicated by a solid line. And here it is going to be a primary valency here, and it is a variable valency, while the secondary valency is a fixed valency. Primary valency has no direction, secondary valency has direction, gives rise to the exact geometry of the molecule. And secondary valency is non-ionizable and it is satisfied by either neutral molecule or negative ions, you can say ligands. Primary valency is satisfied by counter ions, secondary valence are satisfied by ligands, we can say. And yeah, I like your emojis and all, keep giving emojis. Okay, Rubira, some name is given, I am not comfortable to pronounce that name, no worries, but I like your admiration and all. So secondary valence is equal to the coordination number and it is fixed, while primary valency is not fixed, it is a variable valency. But here the metal and ligand, the secondary valencies and the primary valencies are shown together like this. And example, you can see this is going to be primary valency and this is going to be your secondary valency. Inside the square bracket is said to be secondary valency, outside the square bracket is going to be the primary valency. That is a noteworthy point, you can just go ahead with that. And here you can say Mn Cl2 H2O6. In that 2 primary valencies and 6 secondary valencies are being seen. And secondary valency, in the coordination polyhedra, the ions are group bound to the secondary linkages to the metal have characteristic spatial arrangement, so that geometry of the complex compound is based on the secondary valency. ठीक है बेटा, अगर कुछ डाउट है ना तो आप चार्ट बॉक्स में पूछ सकते हैं. जो स्टूडेंट्स हैं अभी, प्लीज लाइक द सेशन. व्हेन यू क्लिक द लाइक बटन ना, इट विल बी ऑटोमेटिकली विजिबल टू मी एंड सेशन का जोश भी बढ़ जाता है. ठीक है बेटा. Now let us talk about CONH3 6Cl3. It is a compound. Cobalt chloride is dissolved in ammonia and recrystallized in different temperatures, gives rise a series of compounds that is given by Werner. Werner is said to be the father of coordination compounds, and he is the one who studied cobalt chloride with ammonia salts, and that different salts is said to be Werner series. And let us see this Werner series mein, so 6 ammonia are there, so that 6 primary valency, and 3 chlorines are there, and 3 chlorines are going to be the primary valency and ammonia is going to be secondary valency. And in that way, different compounds, CONH3 5 times, Cl, Cl2. Now the chlorine that is shown here, 3 chlorines, 2 chlorines becoming the primary valency, 1 chlorine is going to be the secondary valency, because the coordination number जो 6 है ना is हमेशा fix होता. In some books it is written क्लोरीन ए जो प्राइमरी भी हो सकता है, सेकेंडरी भी हो सकता है, ऐसे दिखा देंगे. राइट बेटा. एंड अंडरस्टैंडिंग दिस इज वेरी इंपॉर्टेंट. एंड आई वांट टू से हियर, when this particular complex is dissolved in the water and it is precipitated with AgNO3, 2 moles of AgCl is going to be precipitated. That number of moles of AgCl precipitated can tell the information about how many chlorines are there outside the square bracket. समझ में आ रहा है क्या बेटा? Based on that आप प्राइमरी वैलेंसी का नंबर निकाल सकते हैं, सेकेंडरी वैलेंसी का नंबर ऑटोमेटिकली इट इज गोइंग टू बी 6. ओके, पंकज and Sunita Devi, right, Rubira, and we can see here one more here, just only 1 chlorine is there in the outside the square bracket, so we can say only 1 primary chlorine, so 1 mole of AgCl can be precipitated. And NEET 2025 में conductivity order भी दिया. So number of ions, conductivity order is directly proportional to the number of ions. Now I want to give you the clear picture about the primary valency and the secondary valency. Bacho, you can just see the differences between the primary valency. It is denoted by dotted lines and secondary valency is denoted by a solid line. And primary valency is equal to oxidation number and secondary valency is equal to coordination number. Primary valency is ionic bond है, so इसका direction कुछ भी नहीं होगा. While the secondary valency is a covalent bond, it has a direction. And primary valency is ionizable, secondary valency is non-ionizable. So any doubts? And based on that, Werner's the most common geometrical shapes that you can see from the various coordination number. अगर coordination number 6 होगा तो octahedral होगा, coordination number 4 होगा तो ये tetrahedral भी हो सकता है, square planar भी हो सकता है. Okay, while and moving ahead, octahedral complex, tetrahedral complex and square planar complex. A simple diagram को आपको दिखा देना चाहता हूँ. Moving ahead here, I want to say on the basis of these observations, okay, a question कैसे निकाल सकते हो बेटा, and assign the secondary valences to the metal in the following compounds: PdCl2 4NH3. Okay, if this is treated with excess AgNO3, 2 moles of AgCl is getting precipitated, so that 2 chlorine should be outside the square bracket, so that I can say PD NH3 4 and it is going to be Cl2. Similarly, nickel H2O and it is going to be 6 and 2 chlorines are going to be outside the square bracket. And this has no AgCl is getting precipitated. So, this is going to be PtCl4 and PtCl4 you can say H2O. You can say like this. So, there is no chlorine and COCl3 4NH3. This is a little tricky here among 3 chlorines. So, PT NH3 and you got it is 4 here. Among 3 chlorines, 2 chlorines are inside the square bracket, 1 chlorine is outside the square bracket, ताकि इसका 1 chlorine getting precipitated. So, like that in the boards as well as a NEET you can answer the questions, and if you see the answer it is going to be like this. And here the volume in milli, okay, that we'll discuss it later. Okay, limitations of Werner's theory. So, we'll discuss the questions and we'll complete the concepts first. And limitations of Werner's theory. Why only certain elements possess the remarkable property of common coordination compounds, that is transition elements. Why the bond in coordination compounds has a directional property is not explained, and cannot explain optical property as well as a magnetic property. Why I am telling this? Which of the following is the limitation of the Werner's theory? And theory oriented question will be given. You have to check which is the correct property, which is explained, which is not explained. अगर कुछ doubt है ना तो जल्दी पूछना. Right. Moving ahead, Valence Bond Theory. It was developed by Linus Pauling, double Nobel laureate. One is in the economics he got it, and Nobel Peace Economics में है and chemistry में है. Valence Bond theory is extended to coordination compounds by Linus Pauling. He is talking about the hybridization is the key point. And according to this formation, the various postulates I will discuss here. According to this VBT valence bond theory, the coordination compounds will have a type of bonding. Formation of a complex involves the reaction between the Lewis base, a donor, that is ligand, to this Lewis acid, the metal atom, with the formation of a dative bond. Otherwise you can say it is a coordination covalent bond. According to VBT, the bond between metal and the ligand is a dative bond. Everybody accept this. And I want to say the postulate to VBT utilizes the concept of hybridization. So, in which n minus 1 d orbitals can be used and ns orbitals can be used. And a set of equivalent orbitals are going to be generated. So, those hybrid orbitals are allowed to overlap with vacant d orbitals, and vacant hybrid orbitals are going to be allocated so that ligand can come and donate an electron pair to form a dative bond. That is the key point. So, here there are some glitches and unclarified things are there. So, the number of unpaired electrons measures the magnetic moment of the compound, determines which d orbitals are being utilized. Actually, this theory just explained basis on the magnetic moment. The complex is taken and its magnetic moment is calculated. Based on that magnetic moment is d orbitals are manipulated to get a relevant hybridization properties. So that is the key point. Everybody look at this here. The hybridization and the shape of the complex can be predicted with the help of the known properties, just like a magnetic moment. You know what is the magnetic moment is equal root over n into n plus 2 Bohr magneton, where n is equal to, tell me, number of unpaired electrons. Number of unpaired electrons. Okay? Fine. Now look at this. If a coordination number 2, okay, type of hybridization is SP. If it is a 3, SP2, shape is going to linear trigonal. Generally with this kind of hybridization we don't see in common examples. If it is going to be coordination number 3 or 4, it could be either tetrahedral or square planar. So that makes the basic difference and lot of confusions with our students. So bacho, confusion I am going to remove that, and let us see this type of hybridization is sp3, it is tetrahedral. So in that d orbital istemal kiya nahi. And you can see, do you know any other type of hybridization with the coordination number 4? We know it is coordination number 4 is going to be tetrahedral. Tetrahedral everybody knows is sp3 hybridization. But with coordination number 4, you can expect sp3, dsp2, d3s also. So of course this is not that great importance in our discussion, but these two are going to be super important for this. So if it is sp3, you can say it is a tetrahedral. If it is a dsp2, it is going to be square planar. In that कौन सा d orbital इस्तेमाल किया जाएगा? You can say dx square and y square orbital इस्तेमाल किया जाएगा. That's a very important to extract 1 mark in the NEET examination, and this is a catchy point. Which of the following d orbitals are being used in dsp2 hybridization? dx square and y square. And also coordination number 5 chhod do, and coordination number 5 is not that important. Okay, so let us talk about the coordination number 6. Coordination number 6 means it could be sp3d2 or d2sp3, two types of hybridization. For 4s, 4p, 4d orbitals are being used, sp3d2. 3d, 4s, 4p orbitals are being used, d2sp3. ये दोनों में dz square, dx square, y square orbital इस्तेमाल किया जाएगा. That is very very important. And both are going to have sp3d or d2 or d2sp3. coordination number 6 का octahedral complex बनेगा. This happens, outer d orbitals are being used by weak field ligand, weak ligand. This happens when inner d orbitals are being used. This happens with strong ligand. So हमको कैसे पता चलेगा ये strong ligand है, weak ligand है? Now mention your doubts in the chat box. So let's see the example of different coordination numbers. Can we? Yeah, I am explaining you the various complexes that can be formed. Now let's see here, coordination number 2, 3, 4, 5, 6. My emphasis, I want to go here coordination number 4 and I want to give coordination number 6. Coordination number 6 वाला काफ़ी important है. So if it is okay, coordination number 4, directly I want to go into that. Yes, coordination number 4. Coordination number 4. In this, nickel Cl4 2 minus. Experimental magnetic moment is, first it is taken and experimentally it is calculated as 2.5 Bohr magneton. Bm is Bohr magneton, so it is paramagnetic. So it has 2 unpaired electrons. These 2 unpaired electrons आने के लिए hybridization कौन सा चाहिए आपको? So that nickel का जो 3d8 4s0 4p0 nickel 2 plus का So 3d8 का जो electron configuration है ना, it comes like this, so that s orbital 4p 3p orbitals of 4p are being combined, so that Cl minus एक electron pair देके, and these are all paired electrons. So this one and this one become unpaired electrons. So it undergo sp3 hybridization, and mu is equal to root over n into n plus 2. It is equal to root over 2 into 2 plus 2. Okay, so root 8 milega. So that's what 2.84. The same thing you can see whenever you can see this is hybridization is sp3, it is tetrahedral. जब sp3 आता है ना, hybridization is going to be tetrahedral. Fine. Rubira and Sunita Devi and Pankaj, if you have any doubts, please let me know quickly. This is a very important class. Now moving ahead, और एक example था ना, nickel tetracyanide, tetracyanonickelate 2. If you take this particular complex and put in this gauge meter, so magnetic moment experimentally is observed to be 0. So that I want to say it is a diamagnetic. If experimental magnetic moment, if mu is equal to 0, diamagnetic. If mu is greater than 0, it is going to be paramagnetic. Fine. So let's see here. In this nickel 2 plus 3d8 4s0. Now this is a 3d8. So 3d8 means you can say 1, 2, 3, 4, 5. Okay. So this is a 3d8. 1, 2, 3, 4, 5, 6, 7, 8. So what will happen? These two orbitals, this is the orbital is going to jump from here to here, so that these are going to be paired here, so that it become vacant. So one s orbital, one d orbital and two p orbital are going to join together, dsp2 hybridization milega. So it is going to be dsp2 hybridization. Inner orbitals are being used, so that it is going to be a square planar complex, so that its total magnetic moment is going to be low because of the less number of unpaired electrons. So it is called as low spin complex. So that as there is no unpaired electrons found here, so n is going to be 0, mu is equal to root over n into n plus 2. So mu is equal to 0 hoga. It is going to be diamagnetic. It is going to be diamagnetic. Fine. Ganesh, yeah, what is your doubt? I want to ask you, then I can reply. Ganesh, so if I can understand your question, I can reply you. Moving ahead here, so this is hybridization sp2 dsp2 beta, and it is a square planar, and the magnetic moment is going to be diamagnetic property. It is going to be diamagnetic. Fine. And also inner orbital complex is a common phenomena that you can see whenever a strong ligand is there, the d orbitals are going to rearrange. So the complex formation, the inner d orbitals being used during the hybridization. Ganesh, आपका doubt क्या? Where is your doubt? You said please reply. I replying your doubt if you present your doubt. And outer orbital complex, outer d orbitals are being used, is called as outer orbital complex. Okay. And it is not complex. Let us see coordination number 6 वाला का देखना है अभी. So let us focus on the crystal field theory now. And before going for this, inner orbital outer orbital कब होगा? देखो inner orbital outer orbital कब होगा? Inner orbital happens when strong ligands are there. When strong ligands are there. Fine. How do I know strong ligands? Cn minus NH3, okay, C2O4 2 minus, these are all strong ligands. Carbon is the donor, nitrogen is the donor, are going to be strong ligands. Outer orbital complexes. Outer orbital complexes we discuss. Here outer orbital complexes is going to be weak ligand. Whenever weak ligands are coming, you can say it is an outer orbital complex. How do I know this weak ligand? Whenever F minus, Cl minus, Br minus and I minus and H2O. These are all outer orbital complexes. Okay. And how do I know this is the outer orbital, inner orbital complex? Valence bond theory cannot explain that. I am going to explain you now about the crystal field theory. So far you learned about the valence bond theory. Bachcho, we discussed about the conclusion of Werner's theory, primary, secondary valencies and valence bond theory, example of different coordination numbers also we have seen. Now you are going to see the limitations of VBT and crystal field theory, spectrochemical series, crystal field splitting in the octahedral complex. So that is my agenda for the next 30 minutes of the class. Okay, beta? And you can see this is the coordination number 6. CONH3 6 3 plus, its magnetic moment is going to be 0, so it is going to be diamagnetic. So to get this diamagnetic property, I want to take the cobalt electronic configuration. 6 electrons are coming like this. 3d6 means like this. 1 2 3 4 5 6. So NH3 being a strong ligand, NH3 being a strong ligand in this electron is coming and jumping here. Okay, so it is coming and jumping like this. I will show you that. This electron jump here, this electron jump here. So the two orbitals become vacant. So two d orbitals and one s orbital, 3 p orbital मिला के d2 sp3 मिलेगा. Inner orbitals are being utilized. So it is going to be low spin complex. So you learn like this, you never forget. So that it is going to be d2 sp3 and octahedral. Are you getting or not? Electron pairs are seen with the ammonia like that, and there is no unpaired electron, it is going to be diamagnetic. If you can see here, coordination number CO with the same cobalt, COF6 3 minus. Now its magnetic moment is going to be 4.9. If we just take this 4.9, N is equal to 4. So to make this 4 unpaired electron, cobalt same 3, 3d6, d6 and outer orbitals are being used. When it is used outer orbitals, you are going to see electron pair of the F minus is given here, here. So I can see 1, 2, 3, 4 unpaired electrons are seen. It is going to be paramagnetic. Okay. So it is going to be paramagnetic, bachcho. These examples are there in the NCERT. These examples are there in the NCERT. If you talk about COF6, it is going to be outer d orbitals are being used and it is octahedral and it is. So here what is the limitation here? You can check it. It involves lot of assumptions, but Linus Pauling got Nobel Prize because of assumptions. It does not give a quantitative interpretation. interpretation of magnetic moment data. Okay, it does not explain the actual color of the compounds that is exhibited. The reason behind the color exhibition is not explained. Right, Bacho, let us see more details about this. So it does not give a quantitative interpretation of thermodynamic and kinetic stability. It is not explaining the stabilities of the complex compounds. And it does not make an exact predictions of tetrahedral and the square planar complex with the coordination number 6. It does not establish between the difference between a weak ligand and a strong ligand. It is an assumption which is a strong ligand, which is a weak ligand. So textbooks will tell you the list of strong ligands and the list of weak ligands, we follow that only. Right? Bacho, let us see. Moving ahead, you can see various examples. Yeah, crystal field theory. It is also taken into the again assumptions. First basic thing is valence bond theory is the metal to ligand bond is a covalent bond according to valence bond theory. But according to crystal field theory, the metal to ligand, the bond is ionic bond. Electrostatic model, ionic bonding model. So let us see that according to the electrostatic model or the metal ligand bond is ionic and considered purely electrostatic attractions to the metal in the ligand. When the ligands are anionic ligands or neutral ligands, you take anionic ligands, you can say Cl minus, it's a point charge. When you take neutral molecule like ammonia, it is going to be a point charge, point dipoles. When this point dipole is approaching the metal, metal has 5 d orbitals, dxy, dyz, dzx and dx square, y square and dz square. And these 5 d orbitals have the same energy, but these point charges are coming and approaching this metal. It is going to lose its degeneracy, and this d orbital is splitting into 2 set of orbitals. One is with a lower set of orbitals and another one is with a higher set of orbitals. That is the main course of this crystal field theory. So the positive point charges, and when the ligand is coming and approaching the ligand metal, so actually the dipole is coming and charging. So you can have ion-ionic interaction or ion-dipole interaction, right? So in the isolated gaseous metal ions or atoms, the 5 d orbitals has the same energy, mean to say degenerate. Orbitals having the same energies are said to be degenerate orbitals. And orbitals are identical energy. So 5 d orbitals has the same energy, they are called degenerate d orbital free metal atom comp. Whenever the ligand is coming, there will be a repulsion among these orbitals. So the degeneracy is still maintained in spherical symmetrical field of the ligand surrounds the metal atom or ion. Fine. The moment the degeneracy of the d orbitals are seen, overall energy is just increased, the metal and ligand is approaching. Okay. After this, what happened? When the moment ligand start binding with the metal, the degeneracy is lost. Fine. When the degeneracy is lost, either anions of the negative and dipolar molecules like NH3, lone pair of electron is there, and water lone pair of electron is there. When there is a negative field due to the ligand in the complex, okay, it becomes asymmetrical and the degeneracy of the d orbitals is completely lost, result in the splitting of the d orbitals. So there will be energy gap among the d orbitals that is happening in these complexes. So d orbitals split into 2 set of orbitals. Okay, that is lower set of orbitals comes to be dxy, yz and zx. They are said to be and dx square, y square and dz square. And they are going to be Eg and T2g orbitals, and the energy gap between these two is said to be octahedral crystal field splitting energy, delta O you can see, and the middle one is called Barry center or Barry line. Fine. And So the properties like electromagnetic spectra and the color, the magnetic moment can be determined by using this crystal field theory. Crystal field theory gives an idea about electronic distribution of the central metal ion in the given complex. That's a fantastic phenomenon. And crystal field splitting depends on two things. One is ligand, another one is metal ion. So, bacho, this is a live interactive session. I want to address one thing here. So, you prepared your NEET examination throughout the year, but this is the time for this board examination. So, we don't want to leave you. You definitely keep NEET examination preparation aside and focus on the board examination right now. But the thing is, the board examination करने का वक्त में NEET भी आप कर सकता हूँ, and this is how. And in this one shot sessions, what we are doing in a CBSE preparation, and we will be talking about both the things, and automatically your CBSE NEET is going to be revised by me, and you will be having a question to understand and you revise the things. And however you do good, sometimes during examination pressure will be there, so you focus more on the pressure management now, right? So no doubt, Shruti, so I request those students who are online, please like the session. So if when you press the like button, automatically it will be visualized, so that session का जो जोश है ना वो बढ़ जाता. Okay, moving ahead here, some ligands are able to produce a strong field, some ligands are able to produce a weak field. So splitting will be strong field means, you can see these 5d orbitals are there na, strong field, it is going to split like this. If it is, this is a strong. If it is a weak, what will happen? So these d orbitals appears like this. The energy gap will be very less. Energy gap will be very less, right? Energy gap is going to be too large. So this is a weak ligand presence, it is a strong field ligand presence. Okay, Shruti, fine? But moving ahead, generally ligands can be arranged in increasing order of this splitting of the field strength. So such series is called as a spectrochemical series. You have two types of series. One is electrochemical series you studied in electrochemistry. This one is a spectrochemical series you study in the spectrometry in the crystal field theory. That is given as I minus less than Br minus less than S2 minus E NCRT के हिसाब से दे दिया. But here the problem is how to memorize this one. You talk about this H2O. Anything are going to be the strong ligands, anything is going to be the weak ligands. But here I want to say here, generally they are strong field ligands and generally you can see the weak field ligands. But I can say the order of the strength of the ligand can be based on C donor is more than N donor is more than O donor is more than halogen. So if you see this order, you are going to see the which is going to be the strong ligand, which is going to be the weak ligand. Fine, hope you understand this. Now, halide donor are the weak donors, oxygen donors, nitrogen donors and carbon donor, pattern of increase in sigma donation. And this is the trick, you can follow it. You can follow while doing your CBS examination as well as NEET examination. Fine. If you have any doubts, please let me know. Now, splitting of different types of complexes, you can just see crystal field splitting in octahedral complex, tetrahedral complex and square planar complex. In that, octahedral complex काफी important है बेटा. Directly you can get a question from there. Okay, Sunita Devi and Pankaj and Ruber and Ganesh, Srishti. Let us see, talking about in the octahedral complex. There are 6 ligands will be there in octahedral complex. Coordination number is going to be 6. So, electrons in metals and d orbitals, and there is an electrons, negative charges of the ligands, there is a repulsion among them. Therefore, what happened? So, these directed d orbitals directed towards the ligand, so that they will experience more repulsion. Energy is increased with respect to all the d orbitals. They are dx square y square orbitals are going to be more repelled as compared to the xy, yz, zx orbitals. So that what happens here, to understand the shift of energy orbitals, let's first see the structures of d orbitals. In this d orbitals, you can see dxy, yz, zx, and they are directed between the axis, and they are directed along the axis, so they experience more repulsion. They experience more repulsion, they experience less repulsion. समझ में आ रहा है क्या बेटा? So that more repulsion means they are going to energetically high, less repulsion means they are going to be energetically low. Fine. And the degeneracy of the d orbitals has been lost due to the repulsion. So, yield 3 set of lower energy orbitals, they are said to be T2G orbitals. So, this is XY, YZ, ZX orbitals. So, they are going to be lower set of orbitals. They are XY, YZ and ZX. They are said to be T2G orbitals, and they are going to see 2 set of orbitals, EG orbitals. So, X square and Y square and Z square. Fine. And this is happening in the octahedral complex. So, this is called crystal field splitting in octahedral complex. Are you getting or not? Crystal field splitting in octahedral complex. And ligands approaches from towards the axis, and orbitals present towards the axis will be repelled, that is dx square, y square goes at the higher energy, and they are said to be TTG orbitals, and you are going to see, and dxy, yz, gx orbitals are going to be typically degenerate, still they remain in the low energy. Orbitals of center of symmetry can be seen. Moving ahead, dx square, y square, g square is said to be EG orbitals. They experience more repulsion. T2G orbitals experience less repulsion. So, d orbital splitting in octahedral complex is seen like this. Average energy, and this is called crystal field energy, splitting energy, the energy gap between T2G orbitals and EG orbitals. And between these 2/5 and 3/5 part of octahedral splitting energy is seen. Bacho, doubts? So, I am going to explain here the unpaired electron and electron configuration. So, splitting in octahedral complex. So, splitting of the degenerate d orbital due to presence of ligand is defined the geometry. The energy of separation between T2G in EG is said to be CFSE for the octahedral complex. It is indicated with O, is called for the octahedral complex. Moving ahead, splitting in the help of orbital diagram. and again barycenter is seen if unpaired electron is there. So the unpaired electron should be present in the T2G orbital. So in the presence of a strong ligand, the gap between T2G and EG orbitals gap is so high, so that first T2G orbitals are filled, then EG orbitals are filled. In the presence of weak field ligand, the gap between these two set of orbitals is very less, so that you have to follow Hund's rule. Here in the presence of strong field ligand, the Hund's rule is violated. So T2G orbitals and d electrons occupy the orbital slightly in accordance with the Hund's rule. So if it is a d4 configuration electronic distribution, fourth electron will occupy singly occupied EG orbital. Okay, fourth electrons will undergo pairing with the T2G orbital like this. And moving ahead here, D4 configuration 2 possibility of electronic distribution. Fourth electron will singly occupied with EG orbital according to the Hund's rule. That happens in the presence of a weak ligand, right? And also fourth electron will undergo pairing with the T2G orbital. That happens in the case of strong field ligand. So that is how you just learn the concept that explains the crystal field splitting. Two possibilities: if the pairing energy is greater than crystal field splitting energy, that happens in the presence of weak ligand. And pairing energy is less than that of octahedral crystal field splitting energy. That happens in the case of strong ligand. So these are the two cases. The same in the square planar complex also you can see that. So let's see the square planar complex. The square planar arrangement of the ligands derived from the octahedral crystal field, removing the two trans ligands located in the z-axis. What is that? Look at this diagram, you will understand. Just like this is up to a octahedral crystal field splitting energy, but here this set of d orbitals is going to split like this. The xy experiences more repulsion, and yz gx comes to be less repulsions. Among this, dx square y square and dz square is going to have dz square is having less than xy, and x square y square is going to be greater than dxy. So this is going to be, whenever it undergo sp hybridization, it is going to be the order of the filling of the electron. So actually this schematic picture I have given for the extra information. In CBS examination, even in the NEET examination, you will be having just coordination number 4, and it could be and coordination number 6, inner orbital complex and outer orbital complex, काफी important है. And you can see more repulsions. So x square y square, the ligand is coming along the axis, so it experiences more repulsion. So generate greater energy, more repulsion. dxy, it is coming in between the axis, energy raised but lower than dx square and y square. dg square, along the axis, lower energy than dxy, while dxg and yz between the axis, so it is going to be the least possible energy. So that's about the square planar complex. So here octahedral crystal field splitting energy of the square planar is always greater than crystal field splitting energy of square planar is always greater than octahedral crystal field splitting energy. It is 1.3 times of octahedral crystal field splitting energy. That's very important. And moving ahead here, yes. Now I want to talk about the factors that influence the stability of the complex. So this is the factor that can give you insight of studying various complexes and various multiple choice questions that you can experience. Stability of complex is directly proportional to CFSC, and it depends on various factors like first oxidation state of the central atom. CFSC is directly proportional to the oxidation state for the same metal. I mean to say Fe3 plus ka is greater than Fe2 plus ka, right? Similarly, K4 FeCN6 iron has +2 oxidation state. K3 FeCN6 iron has +3 oxidation state. High value of CFSE due to its high charge. Fine. Moving ahead, nature of ligand. Strong ligand and weak ligand. You see, strong field ligand will have more CFSC, weak ligand will have less CFSC. So, because of the strength of a ligand can vary this delta O value of the complex. How do I know this CFSC values? Just follow the spectrochemical series. If not, C donor greater than N donor greater than O donor greater than halogen. And the third one, cobalt NH3 के साथ, cobalt fluorine के साथ. So fluorine is a weak field ligand, WFL. So less value of CFSC. And ammonia is having a more value of CFSC. It is going to be with a strong field ligand. Fine. And also geometry of the complex, square planar complex CFSC is greater than octahedral crystal field splitting energy is greater than tetrahedral wala. And various factors that you can see here. So it is an octahedral complex, it is a tetrahedral complex, it is going to be square planar complex. And also you can see nature of metal cation. CFS is directly proportional to size of metal cation. So I mean to say 5d orbital is greater than 4d orbital greater than 3d orbital. Down the group CFSC values of these complexes increases. So these are all the common points that you need to know. So hope you understand. And also factors affecting here, order of CFSC, cobalt, rhodium and iridium. Iridium because it belongs to 5d series, rhodium belongs to 4d series, cobalt belongs to 3d series. Like that you can see gold, silver and copper. Fine. And formation constant Kf or stability constant Ks. Stability is directly proportional to Kf or Ks. For the same metal, a same ligand and fixed coordination number, then only you can use this parameter. So these parameters can help you. So the stability of the complexes, it is given in the different way. Okay. So this is a destabilization constant, formation is equal to, so stability constant. So bachcho, and note greater the value of Kf or Ks value, more is the thermodynamic stability of the complex. So we use the stability this session, and stay tuned and get well prepared and be confident in your examination. Okay, thank you. Signing off, Dr. Suresh, Faculty of Chemistry, signing off. Thank you. God bless you all.